lot of new people to uh, just very quickly, 10 minutes, summarize what we have done and what the issue was and what we need to do in the next couple classes on the biological mass balance. Okay, I mean, so for the people especially who weren't here, what we considered was the following scenario. We have a cell, let us represent it by a circle, let us say in the middle, and we wanted to determine what is the conversion of substrate, oxygen, and nitrogen in an aerobic process for the cell growth. So the cell growth in the presence of oxygen and in the presence of nitrogen from a suitable nitrogen source, for instance, ammonia. And we also specified the limitations of this black box type unstructured approach. From my point of view, I said it doesn't look at any of the intracellular metabolites like NADH and ATP and all, which is part of my, it's been my research work for 30 years. So, of course, it's not satisfactory. And one of my supervisors, he has always believed in structured models. So for him, this approach will not be satisfactory. But what we wanted to show is that even this very simple approach is somewhat useful. It's quite useful to do a overall balance, mass balance for cell growth. And we can write an overall equation. And here we said, unlike the chemical case, we have to include all the stoichiometries, which because we do not know the formulae, unlike the chemical species that you had. We do not know how many atoms of carbon, hydrogen, oxygen, etc., nitrogen are there, let us say, in 1 mole of biomass. So we have to either determine that experimentally, and for our case, we have to represent those numbers in terms of symbols, okay, and balance the equation with the correct stoichiometric coefficients. Okay. Even this I indicated to the students present that even this is somewhat of an approximation because we assumed, I mean, the unstructured overall model for cell growth is also an approximation because we, for the moment at least, we will try to remove this approximation on Sunday. By the way, Sunday we are meeting at 11, right? And we just have to finish this part on Sunday and start the reactive chemical balance. So I indicated that biomass need not be the only product, but we are, for the moment, we analyze the case where biomass is a sole product, and we did a simple mass balance example, which I gave as a problem, and we discussed the solution for it. So what I suggest is everybody, if they can just write the overall balance equation, balanced equation for the elemental balance that we want to do, and then you can always later on consult your colleagues, or you can actually do it on your own also. So the symbols are important because later on Sunday we will again use the same subscript. So substrate we represented by C subscript W, H subscript X, X atoms of hydrogen, O subscript Y, and N subscript Z. So CWHXOYNZ was the empirical formula of the substrate. So this we combusted with A moles of oxygen, O2, molecular oxygen, dioxygen, AO2, and we also can have disparate nitrogen sources because that is an essential element for cell growth. And in principle, this could be of the H subscript G, O subscript H, N subscript I. And there is B moles of this nitrogen source. So B, Hg, OH, and I. And if the nitrogen source is not given to you, I said that you could assume it to be ammonia, okay, a most common nitrogen source. Okay, so this is the left-hand side of the equation. On the right-hand side, we have CO2 and H2O as products. And in this case, biomass as the sole product, or the others are byproducts. This is sole product. We will improve this on Sunday. So the stoichiometric coefficient for the biomass, we write always as small c for the number of moles times c to the subscript 1 for per atom of carbon, H alpha, O beta, and delta. Okay, C, H alpha, O beta, and delta. So C times capital C, H alpha, O beta, and delta was the biomass. And then D times CO2 and E times H2O. That was the right-hand side of the overall equation. And then what we did was, we did all the elemental balance for this system. So we did the carbon balance, we did the hydrogen, oxygen, and the nitrogen. For instance, the carbon balance, there is W gram atoms on the left-hand side, and since biomass contains small c gram atoms and CO2 contains small d, so W was C plus D, right? So like that, we did all the elemental balances. And still we found that we were an equation short to solve for all the stoichiometric coefficients. So can someone tell me who was present? What was, we supplemented it with by what?
So can you repeat the question, please?
Yeah, so we found that the information that we had was nonetheless insufficient to calculate the values of these unknown stoichiometric coefficients.
We gave
So we still needed to supplement it by something. So what did we do?
We specified the respiratory coefficient that can be measured using like physical methods, like
so not coefficient. Respiratory coefficient is a different term. Quotient.
Yeah, respiratory.
RQ. Actually, in redox biology, you encounter a lot of these redox, very complicated 1 electron, 2 electron reactions. That's the complementary part of my own research, because we can spatially and temporally separate the redox side from the ATP side. And I only looked at the ATP side, and one lifetime was not enough to, I wanted to look at the redox side, but the techniques that are used to probe the redox side are completely different from the acid-base catalysis and other techniques that we need to probe the ATP synthesis process. For instance, you need to be an expert in electron paramagnetic resonance. I mean, they're a completely different set of techniques. And here mass spectrometry was helpful, I mean, on the ATP side. So anyway, so you can't do everything, because there are 4 complexes on the redox side. I mean, they are complex 1, NADH reductase is more